Okay. So we're going to have a coulometry today. So just like the electrogravimetric methods that we have last time, okay, this also involves, we could say, electrolysis or electrolysis. Okay, so when we're talking about coulometric methods of analysis, this is based on electrolytic reduction. Okay, reduction or oxidation of an analyte for a sufficient period of time to assure its quantitative conversion to new oxidation states. If we're going to compare the different electroanalytical method that we have discussed so far, so we can divide them into two groups. So one, where we have static conditions, okay, and that's involving what we call the potentiometric method. Now, coulometry is the same as what we call electrogravimetry and voltammetry, wherein we have dynamic methods. Okay, so usually this involves the current passing through the cell. So if we're going to look at this coulometry, this is an electrochemical method based on the measurement of the quantity of electricity. Okay, so when you say quantity of electricity in coulombs, so usually that has something to do with, we could say, the charge. So that's the quantity of electricity needed to convert the analyte quantitatively to a different oxidation state. So what does this mean? Okay, so what this colorimetric method means? So usually it's a group of analytical methods that involves measuring the quantity of electricity. Okay, so that's the amount of electricity that you need to convert the analyte to different state. So like the gravimetric methods, okay, colorimetry has the advantage that that the proportionality constant between the measured quantity, that's the charge in coulombs, and the mass of the analytes can be computed from known physical constants. So because of this, you don't need to do what? Calibration or standardization. So it's not necessary. Okay, so coulometry, just like what we call gravimetric or volumetric procedures, they are usually accurate. And they are usually faster and more convenient than gravimetric method. Okay, and right now, most of these colorimetric procedures, they are easily automated. Okay, so since this is what we call an electrolytic method, so that means you have to apply potential from external source. Okay, so when we apply potential from the external source, what does it mean? You make a non-spontaneous reaction takes place. Okay, so the reaction that is usually non-spontaneous, since there's an outside intervention of it, you're going to make the reaction happen. Okay, so if we're going to look at these colorimetric methods, I think we can look at some of the fundamental things that we have. So we could say in a mixture that contains zinc 2+ and copper 2+, we can convert all copper 2+ to copper metal and leave zinc in the solution. So how do we do that? How do we do wherein we reduce, okay, the copper 2+ to copper metal and leave the zinc 2+ in the solution? So what we usually do, we can have the copper working, acting as a working electrode. We're going to hold its potential at a certain value. That is usually what? more positive than for the reduction of your zinc 2 plus. So in that case, between this, only this one will happen. This one will not happen. Okay? Because if you can remember, what is the one that is usually happening spontaneously? So usually between zinc and copper, usually your zinc is the one that is oxidized. Okay? So that's the spontaneous reaction, right? Now, if you want, wherein only your copper 2 plus will be converted to metal and leave the zinc 2 plus in the solution, so you have to apply a working potential. You have to apply potential, the working electrode, which is your copper, at a certain value that's positive more than the what we call zinc reduction. Now, if you're going to look at this principle, so usually the charge, or what we call the quantity of electricity, that is measured in terms of what we call a coulomb. And we define coulomb as what? The quantity of charge transported in 1 second by a constant current of 1 ampere. So usually, okay, what is the charge of the electron? You still recall what's the charge of the electron? Sino naka-discover yun? The famous what? Ball drop experiment. So this is equals around what? 1.6 something times 10 to the 19 coulomb. Now, they said for a constant current, okay, of amperes for the in seconds, the charge in coulomb is given by this expression. The charge is just equals to current times time. Okay? And for a variable current, the charge is given by this integral. Q equals to from 0 to a certain times, where the current will change with respect to what we call time. So if we have this as the charge, how do we get the Faraday constant? So usually the Faraday constant is just what? Your so-called Avogadro's number, 6.02 times 10 to the 23 electron. That's for every mole of electron. Okay? And every electron has what? 1.60218 times 10 to the 19 coulomb. So what is the charge in 1 mole of electron? I don't know if this is new to you. You're familiar with this value? So this is your Faraday constant. Now, what does the Faraday law said? Hindi ko makita. So the Faraday is the charge in coulombs of 1 mole of electrons. Okay? And the Faraday law relates the number of moles of the analyte to the charge. So we could say that would be what? Na equals to Q times or divided by N over F. So if we're going to look at this what we call method, this is already one of the old methods, okay, or we could say one of the earliest methods that were developed during the what we call electrochemistry era. Okay, although it came, we could say 100 years after Michael Faraday formulated his law. Okay, well, the way that it was introduced, its first applications to the analytical chemistry was made in what, 1917? So that's over 100 years ago, a century after Faraday established the Faraday law. Okay. So if we're going to look at how these definitions can be used to calculate the mass of a chemical species that is formed by an electrode of a current of known magnitude, we can have this problem. So you have a constant current of what? 0.80 ampere was used to deposit copper at the cathode and oxygen at the anode of an electrolytic cell. So you have to calculate the mass of each product that was formed in 15.2 minutes, assuming that there's no other reactions that happen. So what's the first thing that we're going to do here? Okay, we have to look at the Hop reaction. So what do you think happened to your copper? Is it oxidized or reduced? Anyone? Okay, so this is reduced. So this means this is a copper 2 plus 2 electrons forming copper. Now, on the other hand, it says here you have an oxygen in the anode. So if you have the reduction potential, so that's the one that is what we call oxidized. So most likely, excuse me, you have water here, okay, producing 4 electrons and oxygen molecule and 4H plus. So these are, we could say, the 2 Hop reaction that you could see in a given or in this given system. Okay. So what can we say about the equivalence of the mole of copper with respect to the mole of the electron? For every 1 mole of copper, there is what? 2 moles of electrons. Okay. And 1 mole of oxygen corresponds to 4 moles of electron. So that means from the definition of the Q, that would be equals to what? The ampere times 15.2 minutes times 60 seconds per minute. So what is the charge that we have? Anyone?
$729.6.
729.6. So this is ampere times seconds or coulombs. Now, so that is just what we call the charge. The one that's being asked is the mass of each product that was formed. So we can find it from this formula. Where's the previous slide? This one. Wherein we're going to replace that A to the particular species that we have. So for instance, if you have it in terms of copper, so this is equals to Q over N times F. So the Q that we have is the one that we calculate. And then we have here what? 2 moles of electron for every 1 mole of copper. And we multiply it with the Faraday constant, 96,000 or 96,485 coulombs per mole electron. And in terms of oxygen, Q over NF, so we have still 729.6 coulombs. But this time you have what? 4 moles of electron for every moles of oxygen times the Faraday constant for moles of electron. So cancel the one that we can cancel, coulomb, coulomb, moles of electron, moles of electron. So you have here the moles of the copper and the moles of the oxygen. So what do we get? So one would have 3.78 times 10 to the negative 3 moles of copper. And the other one is 1.89 times 10 to the negative 3 moles of oxygen. But we're not done, because the one that is being asked is
Mass.
the mass. So all we need to do is multiply it with the respective molar mass. So the 3.78, so we will not round it up yet. We can add another digit to it, times the molar mass of copper, which I think around what, 63.55, and oxygen 1.89 times 10 or 32. Okay, so giving you, in terms of the grams of copper,
0.24.
0.24, and instead of oxygen, that would be equals to point what?
0.06 T.
0.06. Okay, so that's how we solve this what we call type of problem, giving us the principle of colorimetry. So this is just more on what? Electrolytic problem that you have covered in your Gen Chem or analytical chemistry. Now, if we're going to look at the types of this, what we call colorimetric method, we can put it in terms of this one. Okay, we can really divide it in terms of what? 2 major types of this what we call colorimetric method. Okay, so it can either be the so-called constant current colorimetry, which is the amperostatic, or the controlled potential, which is the potentiostatic. Okay, and in this what we call the current or amperostatic, as they call it, it can be a primary colorimetric analysis or a secondary colorimetric analysis. And in the secondary colorimetric analysis, this is an external generation analysis or internal generation analysis. But usually, this is just your what? Coulometric titration. Now, for this control potential, potentiostatic, that is the primary colorimetric analysis. Or, wait, Both of them can be what we call the titration, a colorimetric titration. We go on. In fact, yun lang yung use niya in this analysis. Okay, like a titration. So the controlled potential colorimetry and the controlled current colorimetry. Now, you may ask, what's the difference between the two? The potentiostatic and the what we call amperostatic. So we could say in the potentiostatic, the potential of the working electrode or the electrode at which the analytical reaction happen or occur is maintained at constant level, such as the quantitative oxidation or reduction of the analyte occurs without involvement of less reactive species in the sample or solvent. Okay. So in a controlled potential, we could say that the working electrode, the potential of the working electrode is maintained at a constant level. Okay, that's why potentiostatic, stationary potential, or the potential is just the same. So here in this method, usually the current is initially high but decreases, okay, rapidly and approaches zero as the analyte is removed from the solution. And the quantity of the charge required that is usually measured with an integrator. Now for a controlled current colorimetry, so the one that is controlled here is of course the current. So you're going to use a constant current which passes through a cell until an indicator signals the completion of the analytical reaction. So the principle that you have here, this is what? A constant potential, and this is what we call a constant current. Okay? And the quantity of charge required to reach the endpoint is then calculated from the magnitude of the current and the time the current passes. And this method has enjoyed wider application compared to the potential. So this is the one that is more applicable compared to that one. Okay. And this is why I said this is more that is used in the coulometric titration. So this is difference in the colorimetric, okay? Now, there is a requirement, the fundamental requirements for both this method. And both of them should have what we call 100% current efficiency. So that means, okay, for these requirements to be met, okay, it means that all the electrons go to participate in the desired electrochemical process. So it means that each Faraday of charge must bring about a chemical change in 1/n moles of analyte, where n is the number of electrons that is equivalent to 1 mole of the analyte. Okay? If not, what will happen? Then takes more current, leading to an overestimate amount of the analyte. So you have to make sure that you ensure this requirement. Okay? Current efficiency of 100% does not, however, imply that the analyte must necessarily participate directly in the electron transfer at the electrode. Okay? Indeed, more often than not, the analyte participates, at least in part, in a reaction that is secondary to the electrode, what we call reaction. So for example, at the beginning of the oxidation, let's say, of Fe2+. So if you have Fe2+, it will be oxidized to what? Fe3+. Okay, so at the beginning of the oxidation of Fe2 plus to Fe3 plus at the platinum anode, all of the currents results from the reaction, Fe2 plus to Fe3 plus. Now, what happened? As the reaction proceeds, what happened to this concentration? Will it remain the same? Class? As the reaction proceeds, ano nangyayari sa Fe2 plus? It will decrease. Okay? As the concentration of the Fe2 plus decrease, however, the so-called concentration polarization will cause. So if you remember from our last meeting, concentration polarization, it will cause the anode potential to rise until decomposition of water occurs as a competing process. So there will be a competing process that will happen. So the concentration polarization will lead to the anode potential to rise, okay, until the water decomposition happen as a competing process. So both of them are what? Reduction, right? So what will happen here? The charge required to completely oxidize all of the iron 2 plus in the solution would then exceed the demanded, the one that is demanded by Curie. And to avoid the resulting error and measured excess of Ce3 plus can be introduced as the start of the electrolysis. And this ion is oxidized at a lower anode potential than water. So your Ce3 plus, it can be oxidized to give you Ce4 plus. And the Ce4 plus that is produced diffuses rapidly from the electrode surface, where it then oxidizes an equivalent amount of the iron 2 plus. So you're going to put on the system that this reaction will continue to take place. And that is, we could say, the concentration polarization. So the net effect here of what we call the electrochemical oxidation of Fe2 plus with 100% current efficiency, even though only a fraction of your Fe2 plus are directly oxidized at the surface of the electrode. We could say the colorimetric determination of the chloride provides another example of an indirect process wherein your silver electrode is the anode, and silver ions, okay, are produced by the current. So these cut ions that are produced, they diffuse into the solution and precipitate the chloride. Okay, so you have a chloride, and what happened? You have a silver electrode, and the silver electrode is converted to silver ion, and the silver ion will react with the chloride to produce the precipitate. And again, a current efficiency of 100%, okay, with respect to the chloride ion is achieved even though this ion is neither oxidized nor reduced in the cell. So that's what we call 100% current efficiency. Here's just, at least in part, the analyte participate. Now, let's go on each of these what we call method. Although we already differentiate the potentiostatic and the amperostatic coulometry. Now, in a controlled potential coulometry, this is the controlled potential coulometry, usually the working electrode will be kept at constant potential that analyze quantitative reduction or oxidation occurs without simultaneously reducing or oxidizing the other species in the solution. So the charge that is required to convert the analytes to its reaction product is determined by integrating the current versus time curve during the electrolysis. So this is the thing. An analysis of this kind will usually has all the advantage of what? An electrogravimetric method, but it is not necessary to what? Weigh the product. So you don't need to weigh the product, because if you weigh the product, that is already electrogravimetry. So this technique can be applied, okay, to a system that yields deposits with poor physical properties, as well as those reactions that yield no solid product at all. So I would say arsenic, you can determine arsenic coulometrically by the electrolytic oxidation of this form of arsenic. Okay, this is arsenous acid to produce what we call the arsenic acid. So I don't know if you have heard this term before. So this is 3. So arsenous acid to arsenic acid. And usually you use a platinum anode. So this is to determine the amount of arsenic in a given sample. And another example here is the one that we have discussed earlier, Fe2 plus to Fe3 plus. You can accomplish it with the suitable potential analyte. So usually what happened here, the current flowing through the cell is proportional to the analyte's concentration. As the reactants are consumed, the current decreases, as you've seen here. And the area under the curve is equal to the number of the columns that is what we call use. So the quantity of electricity is usually measured with what we call an electronic integrator. So there's a means to measure them. Okay, we have this so-called integrator. And if you're going to look at this, as I told you, this is very similar to electrogravimetric method. The only difference is you don't weigh the material. Okay. So you can carry out this potentiostatic coulometry in small volume electrochemical cell using electrode with large surface area or with high what we call steering rates. And if you're going to look at the instrumentation that we have, so usually this looks like this. So you have what? An electrolysis cell, a potentiostat, and an integrator. And if you're going to look at this, how many electrodes do you have? Anyone? If you're going to look at this instrumentation. So how many electrodes do you have here? You can see that you have 3 electrodes. Okay, auxiliary electrode, working electrode, and a reference electrode. So if you're going to look at each of the parts that you have here, so the potentiostat that you have here, that's the electronic device that can maintain the potential of the working electrode at a constant level. Remember, you have to make sure that the potential is a constant. That's why it's a controlled potential colorimetry. Okay, so you need a potentiostat to provide that. So it maintains the potential of the working electrode at constant level with a feedback circuitry which adjusts the potential of the variable direct current voltage source to maintain the potential of working electrode minus the potential of the reference electrode constant. Now, the electrolysis cell usually is consisted of what? The 3-electrode system. So the electrolysis cell, that's where the reaction will happen. Okay? So you have here a working electrode, a counter electrode, and a reference electrode. Oh shit, why did I put the German version here? So if you're going to look at this, is your SCE working reference electrode. This is the stirrer. This is your platinum working electrode. This is a Teflon cup. Okay, and this is the counter electrode. So we could say that is your electrolytic cell. So this is, we could say, a working electrode that contains a platinum gauze. This one is a platinum. Now, on the other hand, this one is a mercury pool. So that's the difference between the two. So you have here the reference electrode. That also contains the salt bridge. So this is the solution. And this is what we call the saturated Coulometric electrode, which is a reference electrode. A stirrer, so the gas is put there. Okay, and then you have the counter electrode. The counter electrode is the auxiliary electrode. So usually your reference electrode are either SCE or silver chloride. And they are both connected to the bulk solution by a salt bridge. And then in addition to that, you have a working electrode. Now the working electrode, we could say, is two types. You have a platinum electrode manufactured from the platinum gauze and fashioned into a cylindrical tube, like the one that you have here. Okay. Or you can have it in form of the mercury pool electrode. So that is what we call the working electrode that you have. Now for the auxiliary electrode, okay, usually this is part of the other half cell, and it's often made from the same material as the working electrode. So if you have platinum, it's often a platinum wire. It's just separated by a salt bridge from the solution containing the analyte. So you separate this auxiliary electrode or counter electrode from the solution in contact with the working electrode to prevent the reaction between species produced at the auxiliary electrode and the species in the bulk solution. Okay, so typically, as I told you, your silver chloride electrode or saturated Coulometric electrode, that is the reference electrode that you have. And the working electrode that you have is either a platinum, if it's in the platinum system, or a mercury. So a means of determining the total charge passed during electrolysis, this is where you have that integration. And usually the one that is in charge there is the so-called integrator, as we call it. One method is to monitor the current as a function of time and determine the area under curve. So I'm not sure. What is the HPLC method that you have there in IC? Is it still Shimadzu? Or meron ng bago? Because if it's still the old Shimatsu, the chromatogram that formed there is an integrator. And I don't know if you're going to believe me or not, there was a time for us to determine the peak area of the sample. You know what we do? We cut the paper and weigh it. So depende dun sa shape ng chromatogram. So obviously, yung mas malaki yung peak area, mas mabigat siya. Okay? But now usually you have a modern instrument, so you can use an electronic integrator to monitor the charge as a function of time, and the total charge can be read directly from a digital readout or a plot of charge versus what we call time. Now, if we're going to look at the schematic of the system for the controlled potential colorimetry, so this is, we could say, the equivalent circuit. Ito lang yung parang mapa ng system mo. So this is the resistance within the cell. So as you could see here, okay, the cell current passes through, that's one here, okay, the current passes to the integrator readout module. That's the readout, something around here, okay, which provides a number proportional to the total quantity of the charge that passes through. So the RS there is the cell resistance between the counter electrode and the tip of the working reference electrode, and the RU is the uncompensated cell resistance between the reference electrode and the working electrode. So if you're going to look how they act here, so this is where the RS here, the cell resistance between the counter and the reference electrode, and the RU there, this is the one between the reference electrode and the working electrode. And then in addition to this, you have the so-called practical circuit. So the practical circuit just shows you the other component necessary in the potential static colorimetry. So if you're going to look at this, so this part that you have here, that's just here. Okay, so you can say, you can put there what the magnetic stirrer, and then the integrator, and then what we call the readout. So parang pinalaki lang to. So you can include here the variable voltage source of the non-inverting input of the operational amplifier. So they have a booster amplifier there. Okay, they supply the high currents that are often necessary, and an integrator and a readout device. Okay, so the presence of the booster amplifier, they have no effect on the potential control circuit. So this is what we call a practical circuit. So among the applications maybe of the majority of the controlled potential colorimetric analysis, it's just involved the determination of the inorganic cations and anions, including trace metals and halide ions. Okay. Now, coulometric potential methods or potential static nature, they have been applied to at least 50 elements of inorganic compounds. And historically, what do you think is the working electrode that they use? Anyone? To analyze these 50 elements. What do you think is the working electrode that they use? Well, it's a choice of platinum and mercury, but mercury has been the one that was used traditionally. So it is what we call mercury as the working electrode. Now, however, in recent years, you try to phase out mercury because of its threat to the environment, and you replace it with platinum. And what do you think? The various form of the carbon. Now, one use of this potential static coulometry, we could say, is in nuclear, what we call energy field, nuclear energy. So what it do? It tries to determine uranium and plutonium. So this widely used in nuclear energy field in spent nuclear fuel to determine uranium and plutonium. So it has a precision of what? 0.06%, which is really good. RSD. Now, in addition to inorganic materials, it's also used for quantitative analysis of organic compounds. As example here, trichloroacetate reduction to dichloroacetate, and of dichloroacetate to monochloroacetate. Okay. You can also use it in organic compounds. It demonstrated that the picric acid, you can reduce it at a mercury cathode whose potential is you can control, and you're able to determine the amount of picric acid at a high accuracy. Now, in terms of instrument, they use it in LC as a detector. So it is an LC detector. So they try to use it to determine organic compounds. So, but the use that it has there is, we could say, limited. Okay. So among the organic compound that it analyzed, we could say guanosine, kynurenine, and those were related with the so-called serotonin. I'm not sure if you're familiar with this one. Are you familiar with serotonin? I know, I heard it. Saan ba ginagamit yung serotonin? Anyone? Mood booster. So it's one of these, what we call what? Neurotransmitter ba yan? Kung mood booster siya. And I'm not sure if it's a good or the bad neurotransmitter, because I know there are several, we could say, neurotransmitter that we have. Right? So it's applicable, we could say, on those that has biological applications. So that is, we could say, the controlled potential coulometry. Now, in terms of the controlled current coulometry, that's the amperostatic. So the way, the principle behind this is the current is kept constant until an indicator signals completion of an analytical reaction. The quantity of charge required to attain the endpoint is calculated from the magnitude of the current and the time of its passage, like Q equals to current times time. So it's known as amperostatic coulometry or coulometric titrimetry. I only did this once when the instrument is still functional at York College. And it happens before the pandemic. But after the pandemic, when we come back, hindi na nag-work your instrument. So that's the problem if you don't use your instrument. Okay. So when you call it a coulometric titration, your electron serves as the titrant. And an example of this titration is the highlights by the silver ions. And it what we call produce at a silver electrode. So the current in your coulometric titration is carefully maintained at a constant. That's why you call it amperostatic. And accurately known level by means of what? So in the other one, we have a potential stat. Here we have the so-called amperostat. And there, they said between the two coulometric method, this has more advantages compared to the other one. First is, if you use a constant current, it leads to a more rapid analysis since the current does not decrease over time. So a typical analysis time for a controlled current calorimetry is less than 10 minutes, as opposed to the 30 to 60 minutes for controlled potential coulometry. And second, with the constant current, the total charge is simply the product of current and time. And a method for integrating the current time curve is not needed. However, there are problems with this amperostatic method. Okay, there's always problem in this what we call method that we have. So as electrolysis occurs, your analyte concentration and therefore the current will also what? Affected due to the oxidation or reduction. So it will decrease, as I told you earlier. So once the reaction proceeds, usually your reactant concentration goes down. And what you need to do to maintain this constant current, the cell potential must change until another redox reaction can occur at the working electrode. And unless the system is carefully designed, this secondary reduction will produce a current efficiency of less than 100%. Remember the requirements that we have, a 100% current efficiency. Now, in addition to that, there's a problem that you need to look on, wherein a method of determining when the analyte has been electrolyzed, okay? So usually in the controlled potential calorimetry, this is signaled by a decrease in the current to a constant background or residual current. But in the controlled current calorimetry, a constant current continues to flow even when the analyte has been completely what? Oxidized or reduced. So continuous pa rin yung flow ng current kasi constant current nga eh. So a suitable means of determining the endpoint of the reaction is needed. And most of these endpoint detection methods applicable to volumetric analysis are equally satisfactory. So what does it mean? Color changes, okay, or the sudden increase or decrease of the voltage, okay? So ang nangyari, para na rin siyang typical na titration method wherein you use either what? An indicator or a pH meter or a voltage meter. So yun yung problema. How are you going to know that the reaction has been completed? Kasi continuous yung pagflow ng current. Now, if you're going to look at the instrumentation of this is really different from the controlled potential calorimetry. So you have here your constant current source. So that is, we could say, your amperostat. And then you have the so-called the cell that contains the electrode. Okay, so you have a working electrode, a counter electrode, okay, on it. So the working electrode usually is what? A platinum. And you can also call it the generator electrode because this is where the mediator reacts to generate the species reacting with the analyte. Remember, your sample is in the solution. So what you're going to do is you're going to react that sample in your solution with something in the electrode. So usually that's your working electrode or the so-called generator electrode. And one requirement that you have there is this one, large surface area. Why? Why does it have to be a large surface area? What's the practical purpose of having a large surface area? Anyone? So you can have the reaction. So if you have a large surface, remember what happened? It participates in the reaction. So if it's a silver, what happened to your silver here? It will be converted to a silver ion and it will react with the chloride that is in your solution. So you produce a silver chloride in the electrode. Okay. Now the counter electrode, on the other hand, is isolated from the analytical solution by a salt bridge or porous split to prevent its electrolysis products from reacting with your analyte. Now, another way of looking at this, if you do the titration, I would say is like this one. Whereas you have a method for external generation of oxidizing and reducing agent in coulometric titration. So you have there the mediator solution. So you have the anode and the cathode here. There's a glass wool. So you have a source of the reducing agent and the source of the oxidizing agent. So here we could say one other necessary instrumental component for this technique is an accurate clock for measuring the electrolysis time, TE, and a switch for starting and stopping the electrolysis. So usually they use what? An analog clock. So imagine you have an analog clock that's accurate to the nearest 0.0 second. Okay, but the need to frequently stop and start the electrolysis near the endpoint leads to a net uncertainty of 0.1 second. So digital clock is much accurate, around 1 millisecond. And the thing is, this switch must control the flow of the current and the clock so that an accurate determination of electrolysis time is possible. Now, most of the application here is what? Titration. And what can you say about the different type of titration here? All of them are the typical titration that you do. So you can have acid-base titration. So maybe you can have here what? Water. So this, what happened to water here? Oxidize or reduce? Okay, so this is reduced. Or you can also have a water that is, we could say, oxidized. Stop. Oh my God. What did I do? So what you have here, okay, there's a titrant generation reaction. Now, what do you think a good example here in the complex symmetric titration? So usually EDTA with a metal. Now, in the redox titration, the classic Ce3 plus reacting with Fe2 plus. So this will be a Ce4 plus here. I think I lost that thing. Now, as I've told you, this is very similar to the typical titration. If we're going to compare the what we call comparison of coulometric titration and volumetric titration, we could say they're really what we call similar. Both of them, they have a detectable endpoint. And they are subject to a titration error. Now, I would say in terms of the difference here, we could say the apparatus and the solution that is employed. So in a coulometric titration, there's a timer and switch that corresponds closely to the burette, and the switch performs the same function as your stopcock. Okay. Now, one difference we could say is in a coulometry, you have the current or the electron generation that serves same functions as the standard titrant solution. Now, the other one, the time, so we could say this is what your titrant solution. Now, with regards to the time, that's the volume that you add. So usually the one that you titrate here is just what? Time and the current. So the amount of the analyte is determined by combining capacity. So the reaction must happen fast, essentially complete and free of side reaction. Now, one advantage of, we could say, colorimetry here is the eliminations of problem associated with the preparation, standardization, and storage of standard solution. Okay. With colorimetry, by proper choice of current, micro quantities of substance can be introduced with ease and accuracy. So what does it mean? It has high accuracy compared to the volumetric method. And the thing with this colorimetric titration, you can have an automatic titration because current can be controlled easily. Now, with regards to the sources of error, there are 5 potential sources of error in a colorimetric titration. You have to make sure that the current that is employed is constant, because if there's a variation in the current during electrolysis, that is a source of error. And as I told you earlier, there should be the fundamental requirements where you have to satisfy the 100% current efficiency. So if you don't satisfy it, there will be sources of error. And then error in the current measurement itself. That's another, we could say, source of error. And then the time. How you measure the time, that is also another source of what we call error. And just like a typical titration, you also have the titration error. So based on Chem 32, titration error is just the difference between the equivalence point and the endpoint. So as you could see, the last of these difficulties is common to volumetric methods as well. So for situations in which the indicator error is the limiting factor, the two methods are likely to have comparable reliability. Okay, another way of, we could say, differentiating the two, you have to do colorimetric titration with a specialized method. And unfortunately, we don't have that in every lab. Now, we can look at some quantitative calculation here. So for instance here, the purity of a sample of your sodium. Anong sulfate to? Is it thiosulfate or persulfate? Okay. Was determined by a colorimetric redox titration using iodide as a mediator and triiodide as the titrant. So a sample weighing 0.1342 grams is transferred to 100 ml volumetric flask and diluted to volume with distilled water. And then a 10 ml portion is transferred to an electrochemical cell along with 25 ml of unmolar Ki, 75 ml of 7.0 phosphate buffer, and several drops of starch solution, indicator solution. And electrolysis has a constant current of 36.45 milliampere, required 221.8 seconds to reach the starch indicator endpoint. So determine the purity. So what's the first thing that we're going to do? We're going to determine the reaction. So you have here this reaction, triiodide producing S4O6 2-. Now the question is, how many electrons do you need to oxidize this to this? Anyone? What is the N? It's only one. So if we're going to look at this, we could say this is what? NF grams of Na2S2O3 over the formula mass of Na2S2O3. So that is, we could say, current equals to the current times the time of electrolysis. So if we're going to rearrange this one, so you have grams of Na2S2O3 equals to ITE cross multiplication formula mass of Na2S2O3 over NF, right? So we substitute it with the value that was given. So what's the current? 36.45. Or we have to make it into amperes. So that's 0.03645. And then time of electrolysis is 221.8 seconds. And then the molar mass of Na2S2O4, so it's around 158.1 grams per mole over. So you have 1 mole and the Faraday constant, 96.485 charge per moles electrode. And what do you get there? One 1.32 or 0.132.
0.0132 po.
0.1. What's up after 2? Ano yung number after 2? Because we need to divide it with this one to get the purity. 0.13247. So we could say 5 para pareho silang, and then multiply by 100. So yan yung purity.
.0 po, sir. 0.0132.
13.2. So how many percentage purity is this? Mali, teka, 0.013 pala. Tama yung ano mo, 0.01325. And then what happened, I think may condition dito, 10 ml is transferred. So we have to multiply this by dilution factor, 10 over 1, right? Or 100 over 10. So times 10. So you end up with 0.1325. Sorry, I skipped that portion. So how many percentage it is?
98.7, sir.
Okay, so it is around 98.7%. So that's just one way wherein it is useful. Now, we could look at the other way here. I think this, if I'm not mistaken, the last slide that I have for tonight is we have this amount of tetrachloropicolinic acid, okay, dissolved in distilled water, transferred to 1,000 ml volumetric flask and diluted to volume. An exhaustive controlled potential. So this is for a controlled potential electrolysis of a 10 ml portion of the solution at a spongy silver electrode requires 5.374 coulombs of charge. So what is the value of N for this reduction reaction? So how do we approach this? So we have N equals to Q over Nm. So if we could say 10 ml, how much of the sample do it contains? So this is what, 1,000.3619 if it's 100.03619 if it's 10. So that's 0.003619. Tama ba ako? So this is around 3.619 milligram. Or we can divide it with the molar mass. You can get the molar mass of this. So you convert this to what? A mole. And once you have that, okay, you can at least use the value here. So N, so Q is what? 5.374 coulomb. Faraday constant is 96,485 coulombs per mole electron. And then we can get the corresponding moles of this one. So based on my notes, I could have this one. So what is the moles or number equals to? If you're going to look at the structure of this looks like this one. So all of them with a Cl. And one is, ano tawag dito? Carboxylate. And then the number of electrons, the one that we're looking for, the N, plus 2H2O, and this becomes this. Kailangan pala ano to, na naka-ring. So this is equals to 4 electrode. So another way to look at the two, so when we're talking about potential static colorimetry, it's more specific than amperostatic colorimetry. But the only problem is it takes longer time, okay, compared to the amperostatic titration. But it's really, we could say, useful. But unfortunately, I don't know anyone there having this coulometric, what we call titration or device there at UP Los Baños. So question. Anong time na? Oh, sakto. So question. Is the canvas back?